There is a place in the universe where an atom stops being a useful picture of matter, not because atoms have vanished from physics, but because gravity has pressed the remains of a star into conditions no laboratory on Earth can reproduce for long. A neutron star can hold more mass than the Sun inside a sphere only about the width of a city. From far away, it may look like a faint point or reveal itself only through pulses of radio waves, X-rays, or gamma rays. Up close, every familiar scale has changed. If you could remain safely above its surface, there would be no broad horizon like the one outside a window on Earth. The star would curve away quickly beneath you. Gravity would be so intense that light leaving the surface would climb outward at a measurable cost in energy, arriving elsewhere redder than when it began. The matter below would not be arranged like rock, ocean, or gas. Even before reaching the deeper layers, pressure would already be forcing nuclei and electrons into forms that belong to a very different physical world. And yet a neutron star is not a black hole. That distinction is the reason it is so valuable to physics. A black hole hides its interior behind an event horizon. A neutron star still has a surface. Light can escape from it. Radiation can carry information outward. Its spin can be timed. Its mass can be measured. In some cases, the shape of its X-ray pulses allows astronomers to estimate its radius. Those two numbers, mass and radius, become clues to something much harder to see: how matter responds when it is compressed beyond the density inside an atomic nucleus. Physicists describe that response with an equation of state. The phrase sounds dry, but the idea is intimate. It tells us how pressure changes as matter becomes denser, and therefore how strongly the material inside a neutron star can resist its own gravity. Different possible forms of matter produce different relationships between pressure and density. That means the size of a neutron star is not merely a measurement of its exterior. It is evidence about what may be happening far beneath the crust. NASA's NICA telescope has helped turn that idea into observation. By measuring X-rays from rotating hot regions on neutron stars, NICA has produced increasingly precise mass and radius constraints. Gravitational wave detections from merging neutron stars provide another view, because each star can be slightly deformed by the gravity of its companion before collision. The amount of that deformation also depends on the behavior of dense matter. Together, these measurements have narrowed the possibilities, but they have not settled the deepest question. We still do not know with certainty what occupies the innermost core of a neutron star. The material may remain dominated by neutrons and other familiar particles under unfamiliar conditions. New particles may appear. Protons and neutrons may begin to lose their identities as distinct objects. Some models allow transitions into more exotic phases of matter. Each possibility changes how the star carries pressure, stores energy, cools, spins, and approaches the maximum mass it can support. The source that led us here follows the same broad scientific question: how far matter can be compressed before its familiar forms give way, and what neutron stars can reveal about that boundary. So tonight, the journey will not begin with a supernova. It will begin at the surface of the object left behind. From there, we will descend layer by layer, following pressure as it rises, matter as it changes, and the rules that keep a collapsed star from collapsing further. The deeper we go, the less certain the map becomes. But the star itself remains above the final boundary. For now, matter is still holding. A neutron star does not begin with a boundary you could recognize as a shoreline or a floor. Its surface is the place where matter finally becomes dense enough to behave collectively as a solid crust. But even that description needs some care. Above it sits an atmosphere so thin that compared with the star beneath, it is almost negligible. Depending on the star's historicity, this outer layer may contain hydrogen, helium, or heavier elements left behind by earlier burning supernova debris, or material drawn from a companion star. The scale is difficult to compare with anything familiar. On Earth, an atmosphere stretches through hundreds of kilometers before fading into space. Around a neutron star, gravity compresses the gas into a layer that may be only centimeters thick. There is simply very little room for matter to remain diffuse. Every particle is pulled toward the surface by a gravitational field tens of billions of times stronger than the one beneath your feet. Even light feels the climb away from this place. Photons leaving the surface lose energy as they move outward through the star's curved spacetime. Astronomers call this gravitational redshift. The effect is not merely a theoretical decoration. It can alter the radiation we observe and provides another way of connecting the visible surface with the enormous mass packed beneath it. From a safe distance, the star may look small. Its gravity does not. The surface itself is also unexpectedly smooth. A mountain on Earth can rise several kilometers because rock is strong enough to resist terrestrial gravity. On a neutron star, even a tiny elevation carries enormous weight. The crust can support irregularities, but their height is limited. What counts as a mountain here may rise only a small distance compared with the scale of terrestrial landscapes. That does not mean the crust is featureless. It is under strain. A neutron star is often born spinning rapidly, carrying with it the angular momentum of the much larger stellar core that collapsed. The same basic principle can be felt when a skater pulls in their arms and rotates faster. Compress a rotating object into a much smaller radius, and its spin can accelerate dramatically. Magnetic fields are compressed as well. A field that once threaded a stellar core can emerge from collapse with a strength far beyond anything counted in ordinary environments. In some neutron stars, the magnetic field becomes strong enough to dominate the behavior of charged particles around the surface. In magnetars, it becomes one of the defining features of the entire object, but the crust itself is still made of matter. At the outermost solid layers, atomic nuclei can remain arranged in a lattice. Electrons move through the structure, no longer behaving like the electrons bound neatly to individual atoms in ordinary material. The pressure is already too great for that familiar arrangement. As you move downward, the nuclei become increasingly rich in neutrons. Gravity keeps raising the density. Electrons are forced into states of higher and higher energy. Eventually, it becomes energetically favorable for some electrons to combine with protons inside nuclei, producing neutrons and neutrinos. The neutrinos can escape, the neutrons remain. This is one of the transitions that makes a neutron star so different from a white dwarf. In a white dwarf, electron degeneracy pressure helps resist further collapse. The electrons obey the Pauli exclusion principle, which prevents identical fermions from all occupying the same quantum state. Compression forces them into progressively higher energy states, creating a pressure that does not depend on ordinary heat. But gravity can eventually overwhelm the support available from electrons. In the collapse that creates a neutron star, the density rises so far that electrons and protons are driven together. Matter is pushed toward a neutron-rich state on an enormous scale, yet this does not happen all at once. A neutron star has structure because pressure changes continuously with depth. The outer crust still contains nuclei. Farther down, those nuclei grow more neutron-heavy until a threshold is reached where some neutrons can no longer remain confined inside them. They begin to leak out. Physicists call this neutron drip. The phrase is almost modest for what it represents. Below this point, matter is no longer a simple lattice of nuclei surrounded by electrons. There is now a sea of free neutrons flowing through the crust alongside the remaining nuclear structures. And because neutrons are fermions, quantum mechanics comes central to the way this material behaves. At sufficiently low temperatures, Many of these neutrons are expected to form a superfluid. A superfluid is not merely a very cold liquid. It is a quantum state in which large numbers of particles behave coherently, allowing flow with properties that ordinary fluids do not possess. Inside a neutron star, such behavior may influence how the star rotates, how it stores angular momentum, and how that rotation changes over time. This becomes especially important when pulsars suddenly alter their spin. Some neutron stars rotate with remarkable regularity, sending beams of radiation past Earth like a celestial lighthouse. Their pulses can be timed with great precision. Yet now and then, a pulsar abruptly spins a little faster. These events are called glitches. One leading explanation connects them to the superfluid inside the crust. But the solid outer layers gradually slow as the star loses rotational energy. The superfluid may not slow in exactly the same way. A difference in rotational speed can build between the two components until angular momentum is transferred suddenly from the interior to the crust. From Earth, the result is a tiny jump in the pulsar's rotation. A change in timing becomes evident about invisible matter kilometers below the surface. The crust, therefore, is not simply the shell around a more interesting core. It is part of the experiment. Its strength affects how the star can deform. Its superfluid neutrons may participate in glitches. Its composition influences how heat travels outward, and its boundary with the deeper interior marks the point where the familiar idea of separate atomic nuclei begins to lose its usefulness. Closer to that boundary, another transformation may occur. Instead of remaining roughly spherical, the nuclear structures may begin to stretch, connect, flatten, and reorganize as the competition between the strong nuclear force and electric repulsion changes with density. Simulations suggest a sequence of complex shapes that physicists have given playful names because some resemble familiar foods. But beneath the humor is a serious question. These structures may affect the star's elasticity, its thermal behavior, and even the way neutrinos move through dense matter. And after them, the map becomes less secure. The outer crust can still be described with physics, tested in terrestrial laboratories and nuclear experiments. The inner crust requires more extrapolation. Beyond it lies the core, where the pressure becomes so severe that even the identity of the particles may begin to change. For now, we are still close to the surface. But already, the atom has started to come apart. Deeper in the crust, the neat architecture of ordinary matter becomes harder to maintain. The pressure rises so steadily that nuclei can no longer remain isolated islands surrounded by electrons. More and more neutrons are pushed out of them, forming a background sea through which the remaining nuclear structures are embedded. The distinction between one nucleus and the next begins to blur. This region is still called the inner crust, but the word crust can be misleading. Nothing here resembles stone. The material is dense enough that a cubic centimeter would contain an amount of mass difficult to picture on human scales. The nuclei that remain are compressed into a lattice, while free neutrons move through the spaces between them. Electrons thread through the structure, highly energetic and strongly degenerate, and the star is still not at its core. The forces shaping matter here are engaged in a careful competition. The strong nuclear force tends to bind protons and neutrons together over very short distances. Protons, carrying positive electric charge, repel one another through the electromagnetic force. Gravity supplies the enormous background pressure that drives everything closer. At lower densities, nuclei can maintain roughly compact forms. As density rises, that arrangement may no longer be the one requiring the least energy. Theoretical calculations and numerical simulations suggest that nuclei begin to distort. They may stretch into elongated forms. Those elongated forms can merge into longer structures with still greater compression, matter may reorganize into broad sheets, interconnected networks, or phases in which the roles of dense and less dense regions seem almost reversed. Because several of these predicted shapes resemble food, physicists gave them an informal collective name: nuclear pasta. The terminology sounds playful because the subject itself is so far removed from daily experience that a familiar image becomes useful. Some modeled structures resemble rounded clusters. Others resemble long filaments. Others resemble stacked sheets. More complicated phases can form networks and voids that have no perfect kitchen equivalent at all. The names are memorable. The physics behind them is not simple. These structures arise because matter is trying to satisfy competing demands at the same time. Nuclear attraction favors one arrangement. Electric repulsion favors another. The enormous pressure of the surrounding star changes the balance again. Instead of a clean crystal made of familiar atoms, the result may be a landscape of nuclear material, organized on scales far larger than an individual nucleus, but far smaller than anything visible. If nuclear pasta exists in the forms predicted, it may occupy only a relatively thin region near the base of the crust. Yet that small region could matter greatly to the behavior of the entire star. Simulations indicate that some pasta phases could be extremely strong. The structures may also scatter electrons and neutrinos differently from the more regular lattice above them, influencing the flow of heat through the crust and possibly the way magnetic fields evolve. Even the rotation of the star may carry traces of what happens here. A neutron star does not always rotate as one perfectly locked object. Its solid crust can spin at one rate, while superfluid components in the interior store angular momentum in a different way. To understand why, it helps to linger for a moment on the word superfluid. At the temperatures found inside an old neutron star, the interior can still be unimaginably hot by everyday standards. Yet, relative to the characteristic energies of dense nuclear matter, parts of it can be cold enough for quantum pairing to occur. Neutrons can form pairs. Paired neutrons can collectively enter a superfluid state. That means their behavior cannot be described simply as individual particles bouncing through a conventional liquid. A large population acts coherently according to quantum rules that become visible across macroscopic distances inside the star. Superfluidity has been produced and studied in laboratories on Earth in other forms of matter. Inside a neutron star, however, it occurs under density and pressure, conditions that cannot be reproduced on the same scale. And rotation gives superfluids another unusual property. A conventional fluid can rotate in almost any continuous manner. A superfluid carries rotation through quantized vortices, narrow threads around which the fluid circulates. A spinning neutron star may contain an immense array of these vortices. As the crust gradually loses rotational energy through electromagnetic radiation and other processes, the star slows. The superfluid must adjust as well. Its vortices move, but they may not always move freely. In the inner crust, vortices can interact with the nuclear lattice and may become pinned to it. If parts of the superfluid remain temporarily decoupled from the slowing crust, a difference in rotation can build. Eventually, the balance can change. Vortices may shift or unpin, angular momentum can be transferred, and from a telescope on Earth, a pulsar that had been slowing with exquisite regularity suddenly spins a little faster, a glitch. The change may be tiny, but pulsars are such precise clocks that astronomers can measure it. For a moment, a signal arriving from thousands of light years away carries evidence of a rearrangement inside. Matter we cannot touch. The event is brief. Its interpretation can take years. Different pulsars glitch in different ways. Some recover part of the change over days or months, some retain more of it. The detailed behavior depends on how the superfluid, crust, magnetic field, and deeper interior interact. So glitches have become one of several ways astronomers try to infer the hidden structure of neutron stars. They are not photographs of the interior, they are consequences. And consequences are often all astronomy has. The same is true for cooling. A newly born neutron star begins extremely hot. Over time, it loses energy. Some heat reaches the surface and escapes as electromagnetic radiation. But especially early in the star's thermal life, neutrinos can carry energy directly out of the interior. These particles interact so weakly with matter that they can pass through regions opaque to ordinary light. How quickly the star cools depends on which neutrino-producing reactions are available, which particles are present, whether those particles are paired into superfluid or superconducting states, and how efficiently heat moves through the crust. A temperature measured at the surface, therefore, contains an indirect memory of deeper physics. Again, the exterior becomes a messenger for a region that cannot be seen. This is one reason neutron stars are so useful. They turn inaccessible microscopic physics into astronomical behavior. A change in spin can speak about superfluid vortices. A cooling curve can speak about particle interactions. A measured radius can constrain how compressible dense matter is. A gravitational wave from a collision can reveal how strongly a star deforms before merger. Each observation is incomplete on its own. Together, they begin to narrow the possibilities. Near the bottom of the crust, the nuclei themselves approach the end of their identity. The average density moves toward that of atomic nuclei. There is less and less low-density space, separating one concentration of nuclear matter from another. Eventually, the idea of distinct nuclei arranged in a lattice ceases to be the most useful description. The crust gives way to the outer core. This boundary cannot be visited by a probe. There is no instrument sitting there to mark the crossing. It is a theoretical transition defined by the changing state of matter. Above it, nuclei and free neutrons coexist in structured phases. Below it, matter becomes much more uniform. Neutrons dominate. A smaller population of protons is expected to remain, along with electrons, and, at sufficient density, muons. The exact proportions depend on the equation of state. The word neutron in neutron star is therefore accurate only in a broad sense. The object is neutron-rich, not made exclusively of neutrons, and even those neutrons may not behave as a simple fluid. In much of the outer core, they are expected to form a superfluid. Protons may become superconducting. That combination creates a medium unlike anything encountered in ordinary planetary matter. A superconducting component can carry electric current without the resistance familiar from everyday conductors. In the intense magnetic environment of a neutron star, superconductivity can also affect how magnetic flux is organized and how the magnetic field evolves through the interior. Now several systems overlap. Gravity shapes the entire star. Quantum mechanics determines which states particles can occupy. Nuclear forces govern the interactions among protons and neutrons. Superfluidity changes how rotation is stored. Superconductivity changes how charged matter responds to magnetic fields. General relativity determines the global structure of an object this compact. None of these pieces can be ignored. This is where the neutron star stops being merely a dense object and becomes a meeting place for different branches of physics. For someone resting under an ordinary night sky, none of this is visible directly. A pulsar may be too faint to see without a telescope. Its crust may be thousands of light years away. Its nuclear structures may be smaller than anything the eye could resolve, even if the star were nearby. And still, the timing of a pulse can cross that distance. A few radio photons can arrive at an antenna. A change measured in a fraction of a rotation can reveal that somewhere inside the star, angular momentum moved from one component of matter to another. The scale changes. The connection remains physical, Below the crust, the descent becomes less certain. The outer core can still be described using particles we know well: neutrons, protons, electrons, and likely muons, interacting under conditions far beyond terrestrial experience. But deeper still, density continues to rise. The particles are pressed closer. Their interactions become harder to calculate. The equation of state becomes increasingly uncertain, and the next question is no longer simply how matter is arranged. It is whether the familiar particles themselves remain the right things to describe. Below the crust, matter loses almost all of the structure that once made it recognizable. There are no intact atoms here. There are no ordinary nuclei arranged in a lattice. The pressure has become so great that the distinction between the inside and outside of a nucleus has nearly disappeared. Matter has crossed into the outer core, a region that contains most of the volume of a neutron star and much of its mass. If the crust was a place where nuclear structures were gradually dismantled, the outer core is where dense nuclear matter becomes the background itself. Neutrons dominate, but they do not stand alone. A smaller population of protons remains mixed among them, together with electrons, and, at sufficient density, muons. These particles arrange themselves in proportions determined by a competition between energy, charge balance, and the weak nuclear interaction. The star must remain electrically neutral on large scales. That means the positive charge carried by protons must be balanced by negative charge and other negatively charged particles. But the number of protons is much smaller than the number of neutrons, so the core is not simply compressed ordinary matter. It is an intensely neutron-rich form of matter. This imbalance matters. In laboratories on Earth, physicists can study atomic nuclei containing different ratios of neutrons and protons. They can collide nuclei, measure their properties, and test models of the nuclear force. But even the most neutron-rich nuclei created in experiments exist for only brief periods and contain nowhere near the number of particles found inside a neutron star. The star takes the same physics and extends it into a regime no laboratory can hold. One of the central questions is how strongly nuclear matter resists being made even more neutron-rich. Physicists describe part of this behavior through something called the symmetry energy. The name refers to the energetic cost of moving away from an equal mixture of neutrons and protons. Inside a neutron star, that cost helps determine how many protons remain in the core, how pressure rises with density, and how large a star of a given mass can be. So a measurement of a neutron star's radius is connected through several layers of theory to the behavior of nuclear matter at scales smaller than an atomic nucleus. A star only a few tens of kilometers across becomes a test of interactions occurring over distances measured in femtometers. The difference in scale is immense, yet the two belong to the same physical system. This is one reason the equation of state matters so much. An equation of state does not tell us where every neutron is located. It tells us how the material responds as density and pressure change. If pressure rises quickly as matter is compressed, physicists call the equation of state relatively stiff. If pressure rises more slowly, it is described as soft. A stiffer equation of state tends to support a larger radius for a neutron star of a given mass. A softer one allows gravity to compress the star more tightly. That simple relationship turns every reliable mass and radius measurement into a clue. The difficulty is that many different equations of state can produce neutron stars that look similar from the outside. Two models may agree at lower densities and diverge only in the inner core. Another pair may predict almost the same radius for an ordinary neutron star, but very different maximum masses. The surface does not reveal the answer directly. Instead, astronomers gather many kinds of evidence and ask which descriptions of matter can satisfy all of them at once. There is another complication. The outer core may behave as more than a dense fluid of individual particles. At the temperatures found in mature neutron stars, neutrons are expected to pair with one another. This pairing resembles, in a broad quantum sense, the mechanism behind certain forms of superfluidity. The particles do not disappear. They enter a collective state. A neutron superfluid can move and rotate in ways that ordinary fluids cannot. The same interior may contain protons paired into a superconducting state. That introduces a second large-scale quantum behavior inside a region already shaped by nuclear forces and immense gravity. The star can therefore contain a solid crust, a neutron superfluid, a proton superconductor, highly energetic electrons, and a magnetic field threading through all of them. These are not separate objects sitting in layers without interaction. They exchange momentum, they exchange heat, they influence magnetic evolution. They respond to the star's gradual loss of rotational energy. A change in one component can disturb another. For a pulsar, those interactions can continue for millions or even billions of years. The magnetic field adds another layer to the problem. In ordinary conductors, magnetic fields can diffuse and decay through electrical resistance. A superconducting medium behaves differently. Magnetic flux may become confined into narrow structures. Rather than spreading smoothly through the material, those structures can interact with the quantized vortices associated with rotating neutron superfluid. The details remain an active area of research because the outcome depends on the type of superconductivity, the strength of the magnetic field, and the microscopic interactions among particles. But the broader point is clear. The interior of a neutron star is not simply matter being crushed. It is matter reorganizing under pressure into collective quantum states that can influence the entire object. Even the star's temperature must be understood in this context. A neutron star may be millions of degrees at its surface and much hotter within. Yet, from the perspective of dense nuclear matter, the interior can still be cold enough for pairing to occur. Temperature is always relative to the energy scales governing the particles involved. The same environment can be violently hot by human standards and quantum mechanically cold at the same time. That contrast becomes important when astronomers study how neutron stars cool. Soon after formation, a neutron star releases much of its thermal energy through neutrinos. These particles escape from deep inside the star far more easily than photons. The rate at which neutrinos are produced depends strongly on the composition and fission of the core. Some reactions are relatively slow. Others can carry energy away much more efficiently. Whether those faster processes are possible can depend on the fraction of protons in the material and on which particles are present. Superfluid pairing can suppress some neutrino reactions. It can also open other channels when pairs form or break. So a cooling curve is not just a record of temperature falling with age. It is another indirect probe of the interior. Astronomers compare the estimated ages and surface temperatures of neutron stars and look for patterns that different models can reproduce. The challenge is that real stars come with uncertain histories. Some have accreted matter from companions. Some have stronger magnetic fields. Some may have different crust compositions. Some may have been reheated internally. No single temperature measurement solves the equation of state, but each one narrows the space of possibilities. The same is true of spin. The same is true of mass. The same is true of radius. Neutron star physics advances by combining imperfect clues. There is no single window into the core. Instead, there are several narrow openings, each admitting a different kind of information. X-rays reveal hot regions moving across the surface as the star spins. Radio pulses measure rotation with remarkable precision. Binary motion reveals mass. Gravitational waves reveal how compact objects respond to tidal forces and collision. Thermal emission traces cooling. Glitches hint at internal coupling. Together, these observations begin to describe matter that no detector can sample directly, and the outer core may still be the comparatively understandable part. At densities near those found inside ordinary atomic nuclei, models can be anchored to nuclear experiments and well-tested theory. As the descent continues and density rises, beyond that regime, the uncertainties widen. Particles are pushed closer together than they are inside most nuclei. The interactions become increasingly difficult to calculate from first principles. New arrangements may become energetically favorable. Additional particles may appear. The distinction between hadrons, the family that includes neutrons and protons, and their more fundamental constituents may begin to matter. A neutron is not indivisible, neither is a proton. Each is made from quarks bound together by the strong interaction. Under ordinary conditions, quarks remain confined inside larger particles. No isolated quark has ever been observed wandering freely through ordinary matter. But the center of a sufficiently dense neutron star may approach conditions where the usual boundaries between neighboring neutrons and protons become difficult to maintain. At that point, the question changes again. It is no longer only how compressed neutrons behave, it becomes whether neutrons remain the correct description at all. Other possibilities appear in theoretical models. Hyperons, heavier relatives of protons and neutrons containing strange quarks, may become energetically possible. Meson condensates have been proposed. Some models allow matter to undergo a transition into deconfined quark phases. Others preserve strongly interacting nucleonic matter much deeper into the star. Each possibility changes the equation of state, and each change affects the star above it. A new particle species can provide additional ways for matter to arrange itself. That can lower the pressure at a given density. In other cases, strong interactions may restore resistance and keep the equation of state sufficiently stiff to support heavy neutron stars. This tension is one of the central problems of the field. Astronomers have observed neutron stars with masses around twice that of the Sun. Any proposed interior model must be able to support objects at least that heavy. If a model softens too much at high density, gravity wins too early, and the predicted star collapses before reaching masses that nature has already produced, so every heavy neutron star becomes a boundary condition. It tells physicists that whatever exists in the core must provide enough pressure to survive. That does not reveal the composition. It removes some possibilities and reshapes others. There is a certain patience built into this kind of science. A telescope does not return an image labeled with the particles inside. Instead, light leaves a surface. A pulse crosses interstellar space. A binary orbit repeats. A gravitational wave passes through Earth. And from those signals, researchers work backward toward matter, hidden beneath kilometers of material. The process is indirect, but not vague. Each observation carries constraints. Each constraint changes the map, and as the map moves inward, the confidence gradually thins. The outer core may be dominated by neutrons, protons, electrons, and muons. The deeper core is where that statement becomes less secure. There, the pressure is high enough that the next transition may not simply rearrange matter. It may change what matter is made of. The deepest part of a neutron star is where the certainty begins to thin. Above it, the crust can be modeled using atomic and nuclear physics that connect, however indirectly, with experiments performed on Earth. The outer core is more difficult, but neutrons, protons, electrons, and muons still provide a workable starting point. Deeper down, at several times the characteristic density of atomic nuclei, even that description becomes uncertain. This is not because physicists have run out of ideas, it is because there are too many plausible ones. At these densities, several different arrangements of matter may satisfy what is already known. Some models keep neutrons and protons as the dominant inhabitants almost all the way to the center. Others allow heavier particles to appear. Some predict a transition into matter containing deconfined quarks, and still others describe intermediate phases that do not fit neatly into either category. The star does not tell us which language is correct. It only gives us consequences. One of the first possibilities begins with a simple fact about neutrons and protons. Neither is fundamental. A neutron contains 3 quarks, so does a proton. Under the conditions around us, those quarks are bound together so strongly that they are never observed as isolated particles. This property is known as confinement. Even when high-energy experiments strike protons together, quarks do not simply emerge and remain separate. New combinations of particles form instead. But the center of a neutron star is not an ordinary experiment. Particles there may be compressed until neighboring neutrons and protons are so close that their internal structures can no longer be treated as comfortably isolated from one another. At some density, it is possible that the description in terms of individual nucleons begins to give way to a description in terms of quarks themselves. Possible does not mean established. No observation has yet shown conclusively that a neutron star contains a quark core. Modern equation of state studies still allow several broad families of interiors, including hadronic stars, hybrid stars containing both hadronic and quark phases, and more speculative objects dominated by quark matter. If decoupling occurs, the result would not necessarily resemble the hot quark gluon matter briefly created in particle colliders. A mature neutron star is dense, but relatively cold in the language of high-energy physics. Under such conditions, quarks might organize themselves into paired quantum states. Some theoretical models predict forms of color superconductivity in which quarks near the relevant energy surface pair through the strong interaction. The names can make this region sound more certain than it is. It is better to think of them as candidate maps. Each map asks the same question. If matter enters this state, what happens to pressure? That is the quantity the star cares about. Gravity does not respond to the name of a phase. It responds to energy, pressure, and the way those quantities shape space-time. A proposed exotic core must therefore do more than exist mathematically. It must still allow a neutron star to support the masses astronomers actually observe. And some of those masses are large. PSR J0740 plus 6620 has a precisely measured mass a little above twice the mass of the Sun. Updated NICA analyses place its radius in the neighborhood of roughly 13 kilometers, with uncertainties that remain important. Those measurements tend to disfavor equations of state that make a high-mass neutron star extremely compact, though they do not uniquely determine its interior composition. This creates a useful tension. Many exotic particles or phase transitions can make dense matter easier to compress. When that happens, the equation of state softens. A softer interior may reduce the maximum mass the star can support. If it softens too much, the theoretical star collapses before reaching masses already measured in nature. So any successful model containing exotic matter must find a way to remain sufficiently resistant to gravity. That requirement has shaped one of the enduring problems in neutron star physics. Consider hyperons. Hyperons are relatives of protons and neutrons, but they contain strange quarks. They are familiar to particle physics and have been produced in terrestrial experiments. The question is whether the chemical conditions in neutron star cores allow them to appear in significant numbers at high enough density. Converting some particles into hyperons can become energetically favorable in certain models, but adding new particle species gives matter additional ways to arrange itself. That often lowers the pressure at a given energy density, making the equation of state softer. Then the same difficulty returns. How can a star containing hyperons still support more than 2 solar masses? This is sometimes called the hyperon puzzle. It does not mean hyperons have been ruled out. Instead, it means the interactions among particles must be strong enough or structured in the right way to recover the pressure required by observations. Researchers continue to explore models in which hyperons appear without making massive neutron stars unstable. Quark matter faces a related challenge. A transition to deconfined quarks can soften an equation of state, but it does not have to do so catastrophically. The behavior depends on the interactions assigned to dense quark matter, the nature of the phase transition, and whether pairing or repulsive effects provide additional pressure. Some theoretical constructions can produce hybrid stars with quark-containing cores while still supporting neutron stars above 2 solar masses. So a heavy neutron star does not prove that its center contains ordinary neutrons, and it does not prove that it contains quarks. It tells us that whatever is there must be capable of carrying a remarkable load. That distinction is important. The deepest core is sometimes described as though astronomy is approaching a hidden object that simply needs to be identified. The real situation is subtler. Different microscopic interiors can produce similar macroscopic stars. A neutron star made entirely from hadronic matter may have nearly the same observable mass and radius as one containing a phase transition in its center. Even hypothetical quark stars can overlap significantly with ordinary neutron star mass and radius predictions. This is why radius measurements alone are not enough. They are powerful, but they are part of a larger network of evidence. The mass tells us how much gravity the interior must support. The radius tells us something about how compressible the material is. Gravitational waves from mergers reveal how strongly neutron stars deform in another star's gravitational field. Cooling tells us which energy loss processes may be operating. Pulsar timing can expose rotational coupling. Future observations may reveal signatures of phase transitions during mergers or collapse. None of these measurements needs to solve the whole interior by itself. The strength comes from requiring one description of dense matter to survive all of them. There is a useful way to imagine this without giving the interior a shape we have never seen. Think, instead of pressure, as a thread running downward through the star. At the surface, the thread is anchored to material whose behavior is comparatively familiar. Through the crust, nuclear structure changes. In the outer core, dense neutron-rich matter carries the load. Then the thread enters a region where several possible paths branch away. One path remains mostly nucleonic, another introduces hyperons, another reaches a quark phase. There may be intermediate possibilities we have not yet recognized clearly. But every path must eventually return to the same exterior observations. The star is the test. This is also where quantum chromodynamics enters the story more deeply. Quantum chromodynamics, or QCD, is the theory describing the strong interaction among quarks and gluons. At sufficiently high energies, its predictions can be tested successfully in experiments. At the extremely high densities and relatively low temperatures relevant to neutron star cores, however, calculating the behavior of QCD becomes exceptionally difficult. The mathematics is known, the many-body solution is not. Modern approaches therefore combine nuclear theory, effective descriptions, high-density calculations, laboratory measurements, astrophysical observations, and broad physical requirements such as causality and thermodynamic stability. Even with all of them together, the central equation of state remains uncertain. That uncertainty is not empty space in our understanding. It has boundaries. Recent combinations of nicer measurements nuclear theory calculations, and gravitational wave informations have narrowed the allowed range of neutron star sizes and pressures. They increasingly restrict equations of state that are either too easy or too difficult to compress, but multiple interior compositions still remain compatible with the evidence. The center, then, is not a place where physics disappear. It is a place where several successful pieces of physics overlap without yet forming a single secure picture. Somewhere beneath kilometers of neutron-rich matter, the pressure reaches its greatest value. The particles there may still carry familiar names, or those names may already have become approximations. From the outside, the distinction can be almost invisible. A star can continue rotating. Its magnetic field can continue threading space. X-rays can continue leaving its surface. To an observer, nothing announces that the material at the center may have crossed into a different phase. The evidence has to be drawn out slowly. One mass measurement, one radius, one cooling curve, one gravitational waveform. And that is where the next part of the descent begins, because if the composition of the core is difficult to determine in an isolated neutron star, two neutron stars falling toward one another can force that hidden matter to respond much more strongly. For a few final orbits, gravity squeezes, stretches, and heats them. The equation of state stops being only an internal secret. It begins to shape the motion of space-time around them. When two neutron stars begin their final approach, the hidden physics inside them starts to leave marks on the space around them. For most of their lives, the stars may have remained separated by hundreds of thousands or millions of kilometers, orbiting a shared center of mass, while slowly losing energy through gravitational radiation. The loss is extremely small at first. Their orbit shrinks almost imperceptibly. Then, the separation decreases. The orbital period shortens. The gravitational waves grow stronger. During the final minutes, the motion accelerates until the stars are circling one another many times each second. For an astronomer, this is more than a collision approaching. It is an experiment being prepared by gravity. Each neutron star is compact, but it is not. The gravitational field of its companion begins to distort it. The near side is pulled slightly more strongly than the far side, creating a tidal deformation. The amount of deformation depends on the internal structure of the star. A star made from matter that is relatively difficult to compress resists the tide differently from one whose interior yields more readily. Larger neutron stars tend to be more deformable. More compact stars tend to respond less. So before the surfaces ever touch, the equation of state has already begun to influence the gravitational waves. This information is subtle. The stars are several tens of kilometers across. The gravitational waves may travel for tens or hundreds of millions of years before passing through Earth. By the time they arrive, the stretching they produce in a detector is smaller than an atomic nucleus compared with the length of the instrument, and still the pattern can be measured. On August 17, 2017, gravitational wave observatories detected a signal that changed the study of neutron stars. The event became known as GW170817. Unlike the earlier gravitational wave detections produced by emerging black holes, this signal remained in the sensitive range of the detectors for a comparatively long time. The two objects spiraled together, allowing researchers to follow many cycles of their orbit before merger. The masses indicated that the objects were consistent with neutron stars, but the importance of the event grew almost immediately. Less than 2 seconds after the gravitational wave signal reached Earth, space-based instruments detected a short burst of gamma rays from the same general direction. Then telescopes across the world began searching the surrounding sky. A new point of light appeared in a galaxy roughly 130 million light-years away. Over the following hours and days, astronomers watched its color and brightness change. For the first time, a neutron star merger had been observed through gravitational waves and across much of the electromagnetic spectrum. Different messengers had carried different pieces of the same event. The gravitational waves described the motion of massive objects. Gamma rays marked an energetic event associated with the merger. Visible and infrared light revealed heated material expanding away from the collision. X-rays and radio waves emerged on longer timescales. Together, they created a much fuller picture than any one signal could have provided. For the interior of a neutron star, however, the final moments before contact were especially valuable. As the stars approached, their tidal deformation changed the phase of the gravitational waveform. The effect was small, but it was not arbitrary. It depended on the relationship between pressure and density inside each star. Equations of state predicting neutron stars that were very easy to deform became difficult to reconcile with the observed signal. The merger had reached into the cores without touching them directly. It had used gravity as the probe. There is something unusual about that kind of measurement. Human beings have learned much about matter by bringing it into the laboratories. We heat it, cool it, compress it, accelerate particles into one another, place materials inside magnetic fields, and watch what changes. But no machine on Earth can assemble more than a sun's mass of nuclear density matter and hold it together long enough to examine. A binary neutron star system does this naturally. Then, in its final seconds, it moves the experiment through conditions that no static star can provide. Pressure changes rapidly, matter is stretched and compressed, temperatures rise, the two stellar surfaces meet, and the distinction between one neutron star and the other disappears. The physics after that moment is much harder to reconstruct. The merged object initially contains more mass than either star could have supported alone. Rotation can temporarily help. A rapidly rotating remnant gains additional support against gravity because centrifugal effects reduce the burden that pressure must carry by itself. Differential rotation can provide still more temporary support because different parts of the remnant may rotate at different rates. Thermal pressure also contributes during the hot aftermath. For a short interval, these effects can keep an object alive, even when its mass would be too high for a cold, non-rotating neutron star. But temporary support is not the same as permanent stability. The remnant loses energy. Gravitational waves carry some away. Neutrinos remove heat. Magnetic fields redistribute angular momentum. Material can be thrown outward. As the remnant changes, the support available to it changes as well. Eventually, one of several outcomes may follow. If the remaining mass is low enough, a stable neutron star can survive. If it is above the maximum mass for a non-rotating star, but can still be supported by rapid rotation, the remnant may persist until it loses enough angular momentum. If the mass is too high, even for those forms of temporary support, collapse to a black hole can occur much sooner. The boundaries among these outcomes depend on the equation of state, and this is why mergers offer information about one of the most important numbers in neutron star physics. There must be some maximum mass that a cold, non-rotating neutron star can support. Below that threshold, pressure generated by dense matter can balance gravity. Above it, no static neutron star configuration is possible. Within the usual description of general relativity, the exact value is still uncertain because it depends on the same poorly known high-density physics we have been following toward the center. The heaviest neutron stars provide a lower boundary. They tell us that the maximum must lie above their measured masses. Merger behavior can provide information from the opposite direction. If astronomers can determine whether a merger remnant collapsed promptly survived briefly, or remained stable for longer, that behavior can help constrain how much mass neutron star matter can support. GW170817 became a particularly important case because the total mass of the binary was substantial. Yet the details of the remnant were not observed directly enough to identify its fate with complete certainty. The evidence is consistent with a remnant that eventually became a black hole, but exactly when that collapse occurred remains connected to ongoing interpretation. That uncertainty is useful rather than disappointing. Different possible lifetimes imply different pressures in the interior. A star that collapses almost immediately tells a different story about dense matter from one that survives for hundreds of milliseconds, seconds, or longer. Future mergers observed with more sensitive instruments may make that distinction much clearer. There is another part of the merger that carries information from deep inside nuclear matter. When the stars collide, some material escapes. Tidal forces can pull neutron-rich matter outward before the collision is complete. Other material may be expelled through shock gas during impact or blown away from the hot remnant afterward. Once this matter is released from the crushing pressure of the star begins to expand. Its neutrons participate in rapid nuclear reactions. Heavy atomic nuclei can form. Their radioactive decay heats the expanding debris, producing a transient glow called a kilonova. The light does not reveal the original neutron star core in a simple way, but it connects the merger to another remarkable consequence of dense matter. Elements heavier than iron can be assembled in the aftermath. Some of the gold, platinum, and other heavy nuclei found in the universe can be produced through rapid neutron capture in environments such as neutron star mergers. Matter once compressed into a star, only kilometers across, can eventually spread across interstellar space. Much later, some fraction may enter new clouds. New stars can form from those clouds. Planets can inherit the material. The path is not a return to the neutron star. It is a release from it. For most of the star's existence, gravity holds nuclear matter under pressures that force it into unfamiliar states. During a merger, some of that matter is suddenly allowed to expand. The same particles that had been locked into one of the densest stable forms known in the universe become part of a growing cloud of debris. This is a different kind of boundary. Not the boundary between one phase of matter and another. The boundary between confinement and escape. But near the center of the merged remnant, the opposite process is happening. There, density may climb beyond anything reached inside either original star. If a transition to new forms of matter is possible, the merger may be one of the places where it happens most readily. Some models predict that a strong phase transition could alter the gravitational wave signal produced after the collision. Others suggest changes in the remnant's oscillation frequencies or in the threshold for collapse. Detecting those signatures is difficult. The post-merger gravitational waves occur at frequencies where current detectors are less sensitive. For now, much of that information remains just beyond reach, but the principle is already clear. A neutron star can hide its center while it is alone. During a merger, gravity begins to force the secret outward. The star deforms. The waveform changes. The surfaces collide. The interior is compressed further. And finally, the remnant must reveal, through its survival or collapse, how much pressure matter can still provide. There is no sudden line where physics becomes meaningless. There is only a sequence of limits. One form of support gives way to another. Rotation buys time. Heat buys time. Dense matter supplies pressure. And somewhere beyond all of them lies a mass that a neutron star can no longer carry. The next question is what happens when that final support is removed? There is a limit hidden inside every neutron star. It is not marked by a surface, and it is not a single density that all stars reach in the same way. It is a boundary in the balance between gravity and pressure. Below it, a neutron star can support itself. Above it, no cold, non-rotating configuration can remain stable. This maximum is usually described through the Tolman-Oppenheimer-Volkoff limit. The name comes from work carried out in the late 1930s, when relativistic stellar structure was still a young subject. Richard Tolman developed a general framework for static spheres in general relativity. Robert Oppenheimer and George Volkoff then applied related equations to an idealized star made from neutrons. Their first estimate was far too low because the physics of dense nuclear matter was not yet understood well enough. But the deeper idea survived. A sufficiently compact star cannot be treated with Newtonian gravity alone. In an ordinary star, pressure pushes outward while gravity pulls inward. General relativity changes that picture in an important way. Pressure itself contributes to the gravitational field. The more pressure required to hold the star up, the more that pressure also adds to the source of gravity. This produces a balance with no unlimited solution. You cannot simply keep increasing the internal pressure forever and expect a larger mass to remain stable. At some point, adding more matter causes gravity to strengthen faster than the available equation of state can respond. The star reaches the end of its stable sequence. That endpoint depends on what the interior is made of. If dense matter is relatively stiff, it can support more mass. If it is softer, the maximum mass is lower. A phase transition in the core can shift the threshold. So can the appearance of new particles. The exact value is therefore tied directly to the same unresolved interior physics that has followed us through the crust and core. Observations provide one side of the boundary. Nature has already produced neutron stars with masses around twice that of the Sun, and some measurements extend higher. Any realistic equation of state must therefore support at least those objects. That simple fact eliminates models that collapse too early. It is a powerful kind of measurement because it does not require seeing the center. A heavy pulsar in a binary system moves according to gravity. Its companion moves with it. By timing the pulses with enough precision, astronomers can extract relativistic effects from the orbit. And in further masses involved, the radio signal may have traveled for thousands of years before reaching Earth. But inside its timing is a constraint on matter compressed far beyond nuclear density. Rotation complicates the boundary. The simplest maximum mass applies to a star that is not spinning. A rotating neutron star receives some additional support from its motion. The effect is modest for slowly rotating pulsar, but it becomes more important as the spin approaches the fastest rates a neutron star can sustain without shedding matter from its equator. This means a rapidly rotating star may temporarily support more mass than the non-rotating limit would allow. There is another temporary state created in mergers. A newly formed remnant can rotate differentially, with one region spinning faster than another. It can also be extremely hot. Both effects can help support a mass that would be unstable in an old, cold neutron star. But differential rotation does not last forever. Magnetic stresses and internal fluid motions redistribute angular momentum. Neutrinos carry away heat. Gravitational radiation removes energy. The remnant gradually loses the conditions that were holding it up. If its mass remains above the stable limit, once that support fades, collapse follows. This is one reason astronomers pay such close attention to the seconds after a neutron star. Merger, a remnant that survives for a while, suggests one set of possible equations of state. A remnant that collapses almost immediately suggests another. The lifetime becomes a measurement of pressure. And yet there is no universal visible signal that tells us, with perfect clarity, exactly when the boundary has been crossed. The final transition can be hidden behind hot debris, magnetic fields, relativistic outflows, and the limitations of our detectors. The star can move from supported matter to a black hole without giving us a direct view of the interior at the moment it happens. To understand what that means, it helps to separate two ideas that are often blended together. The first is the maximum neutron star mass. The second is the formation of an event horizon. The maximum mass tells us that no stable neutron star configuration exists for the given conditions. The event horizon marks a different kind of boundary in space-time, one from which light can no longer escape to distant observers. Once collapse proceeds far enough for an event horizon to form, the object is no longer observable in the same way as a neutron star. There is no visible surface sending thermal X-rays outward. There is no crust whose hot regions rotate through view. There is no material boundary from which a photon can climb away and carry information to us. The interior has become causally hidden. General relativity predicts that continued collapse leads toward a singularity under broad conditions, but the word singularity should be handled carefully. In the equations, it marks a place where quantities, such as curvature, become unbounded, and the classical description can no longer be extended in the usual way. It may indicate not that nature has literally produced a simple point of infinite density that we fully understand, but that general relativity has been pushed beyond the regime where it can provide a complete physical description. That is where quantum theory returns. Quantum mechanics has been part of this story from the beginning. It helps explain electron degeneracy in white dwarfs. It helps describe neutron-rich matter and superfluidity. Quantum chromodynamics governs the strong interaction among quarks and gluons, yet general relativity describes gravity on the largest and most compact scales. Both theories are remarkably successful where they have been tested. They do not fit together naturally in the extreme conditions expected deep inside a black hole. So the collapse of a neutron star is more than the end of one stellar object. It moves the problem from dense matter into the unresolved territory between quantum theory and gravity. Before the event horizon forms, however, the neutron star gives us something a black hole cannot. It gives us matter at enormous density that is still exposed indirectly to observation. A surface remains. A magnetic field remains connected to an exterior magnetosphere. Pulses can still leave. X-rays can still escape. The star can still be weighed. Its radius can still be inferred. For this reason, the last stable neutron stars may be among the most valuable objects in fundamental physics. They occupy the region just before gravity hides the experiment. There may also be another possibility in the dense interior before collapse. Some models allow a strong phase transition to quark matter. Others allow hybrid stars, with a core that has changed phase while the outer layers remain hadronic. In some theoretical descriptions, an additional stable branch of compact stars can appear after such a transition. These possibilities are scientifically interesting, but none has been confirmed as the fate of a star pushed beyond the ordinary neutron star sequence. A quark phase, if it occurs, does not automatically rescue a star from collapse. It still requires an equation of state capable of supporting the mass. The crucial question is not whether the matter has acquired a more exotic name. It is whether pressure continues to rise strongly enough as gravity increases. That is the recurring rule beneath every layer of the star. Matter may change form, particles may pair, new species may appear, nuclei may dissolve, quarks may become the better degrees of freedom. But stability always returns to the same relationship between energy density, pressure, and space-time. For someone looking at a neutron star from far away, the threshold would not appear as a line across its surface. The star might continue to pulse, its companion might continue to orbit. The system could look almost unchanged from one rotation to the next, and yet the equations allow only a finite margin. A little more mass from a companion, a little less rotational support. a merger with another compact object. Any of these can move the star toward a region where no stable configuration remains. The breaking point, then, is not a dramatic crack through the crust. It is the disappearance of equilibrium. There is no longer a combination of internal pressure and global structure that can hold the same mass in the same kind of object. The star has reached the end of what neutron star matter can support. Beyond that threshold, gravity does not need to become stronger in some new way. It only needs to continue. And once the surface can no longer remain outside its own gravitational boundary, the experiment changes completely. The next clues no longer come only from the matter inside the star. They come from gravity itself. The interior of a neutron star cannot be opened, sampled, or photographed. So, the search has become a problem of listening to several kinds of evidence at once. One star contributes a precise mass, another offers a radius. A cooling surface reveals how efficiently energy escapes from hidden layers. A pulsar glitch hints at the movement of superfluid matter. A merger allows gravity to deform two stars before they collide. None provides a complete interior map. But the allowed map becomes smaller each time a new measurement arrives. One of the most direct approaches is to measure both the mass and radius of the same neutron star. Mass is often the easier quantity. In binary systems, astronomers can follow orbital motion and use the timing of radio pulses to measure relativistic effects with remarkable precision. Radius is harder. A neutron star is far too small to resolve as a disk with ordinary telescopes. Instead, instruments such as NASA's NICA observe X-rays emitted from hot regions on the surface of rapidly rotating pulsars. As a hot region rotates toward and away from Earth, the observed brightness changes. But the pattern is modified by gravity. As neutron star bends the paths of photons leaving its surface, light from regions that would otherwise rotate out of view can curve around the star and remain visible. The degree of this bending depends on the relationship between the star's mass and radius. Researchers model thousands or millions of X-ray pulses and search for combinations of mass, radius, surface geometry, and temperature that reproduce the observed waveform. From the shape of light arriving at a detector, they infer the size of a star they cannot see directly. NICA has now measured several millisecond pulsars this way, providing radius constraints across neutron stars with different masses. Those measurements are particularly valuable because the mass-radius relationship depends on the pressure of dense matter. A star with more internal pressure tends to resist compression and remain larger. One with less pressure can be squeezed into a smaller radius. The comparison becomes especially useful when two neutron stars have very different masses. If the radius changes only modestly as mass increases, that tells researchers something about how the equation of state behaves across the corresponding range of densities. But radius is only one messenger. Temperature offers another. A neutron star is born intensely hot after the collapse of a stellar core. Over time it cools. Some energy eventually leaves from the surface as photons, but neutrinos can remove enormous amounts of energy directly from the interior. Which neutrino reactions operate depends on the particles and quantum states present inside the star. Some cooling processes are comparatively gradual. Others are much faster. In 2024, researchers examining observations from ESA's XMM Newton and NASA's Chandra identified 3 young neutron stars whose surfaces were considerably colder than expected under slower, minimal cooling scenarios. Modeling showed that their existence favored equations of state permitting rapid cooling in at least some neutron star masses, excluding a substantial portion of the tested possibilities. That does not tell us exactly what occupies their cores. Several physical mechanisms can influence cooling, and uncertainties remain in the star's masses, magnetic fields, ages, and microscopic particle interactions. but cold stars still remove possibilities. A model that cannot cool a neutron star quickly enough has to change or disappear from consideration. This is how the unknown interior is being approached, not through a single dramatic discovery, but through elimination. One equation of state predicts a radius that observations do not favor. Another cannot support a sufficiently massive pulsar. Another produces tidal deformation inconsistent with a merger waveform. Another cannot reproduce the thermal history of a young cold star. Each failure closes one path. The remaining paths become narrower. Gravitational waves provide a particularly different kind of test because they do not depend on light leaving the surface. During the inspiral of two neutron stars, each object develops a tidal deformation in the gravitational field of the other. That deformation alters the gravitational wave signal. The effect depends strongly on compactness, and therefore on the equation of state. GW17RO8177 demonstrated that this information could be extracted from a real neutron star merger, although the event did not identify one unique equation of state. Future observations can add something the first event could not provide with high precision: population. A single neutron star samples one mass. A single merger samples one pair, but a collection of neutron stars spread across different masses can reveal the shape of the mass-radius curve rather than one point on it. That shape may contain evidence of a transition deep inside matter. Imagine increasing the mass of neutron stars gradually. If their cores all remain in the same broad phase, the radius may change in a relatively smooth way. But if matter begins transforming into a different high-density phase beyond some threshold, the relationship could change more abruptly. The effect might appear as a bend, a flattening, or another feature in the population. The exact signature depends on the physics, and detecting it would require measurements precise enough to distinguish a real transition from statistical uncertainty. This is why there is no single ideal neutron star. A low-mass star probes one density range. A heavy star pushes farther into the high-density regime. A rapidly rotating pulsar tests rotational structure. A cooling young star probes neutrino processes. A glitching pulsar provides information about internal coupling. A binary merger tests tidal response and matter under dynamic compression. Each object reaches the core from a different direction. Even experiments on Earth remain part of the same search. Nuclear laboratories study neutron-rich nuclei and collisions between heavy ions. Those experiments cannot create neutron star cores, but they help constrain the behavior of nuclear forces at lower densities. Theory then carries that information upward. Astronomical observations press downward from much higher densities. Somewhere between them, the allowed equation of state must connect both worlds without contradicting either. This meeting of scales is one of the unusual features of neutron star science. Measurements made inside laboratories, only meters across, can influence models of an object 20 or 30 kilometers wide. A radio telescope spanning hundreds of meters can measure pulses from thousands of light years away. An X-ray detector attached to the International Space Station can infer the curvature of space-time near a stellar surface. Interferometers, several kilometers long, can detect distortions in space-time produced by two neutron stars colliding in another galaxy. All of those measurements eventually converge on matter smaller than an atom, and the deepest question remains unresolved. Do neutrons and protons survive as the most useful particles, all the way to the center? Do hyperons appear? Does matter pass through a transition in which quarks become more appropriate degrees of freedom? Are there paired phases or other collective states that alter pressure, cooling, and transport? At present, several possibilities remain consistent with parts of the evidence. The observations have become strong enough to restrict the equation of state but not strong enough to expose one definitive microscopic composition. Modern analyses combine Nike mass radius measurements, nuclear theory, massive pulsars, and gravitational wave constraints, precisely because no individual measurement can yet solve the interior alone. There is something fitting about that. A neutron star was created when a stellar core lost one form of equilibrium and collapsed. Our understanding of it is being built in the opposite direction, piece by piece, constraint by constraint, a radius measured from curved X-ray paths, a mass encoded in orbital timing, a temperature carried by photons from a cooling surface, a tidal response written into a gravitational wave. None lets us descend physically through the crust, yet together they allow physics to descend for us. The boundary of knowledge moves inward, not quickly, not in a straight line, but measurably. And somewhere beneath the surface of every neutron star, hidden beyond the deepest layer, we can confidently describe, matter continues to hold an answer that the universe has not yet made easy to read. A neutron star is not a place where matter has already failed. It is a place where matter is still succeeding. Gravity has taken a stellar core and compressed it beyond the conditions found in ordinary atoms, ordinary solids, and ordinary planets. Electrons have been driven from familiar atomic structures. Nuclei have become increasingly neutron-rich. Superfluid particles may move beneath the crust. Dense nuclear matter carries the weight of more than a sun. And still the star remains outside its own event horizon. That survival is what makes it useful. The question we began with was how far matter can be pushed before the description has to change. There is no single answer. Atoms surrender first. Then nuclei lose their familiar boundaries. Farther inward, neutrons and protons may remain useful descriptions, or new particles and phases may become energetically favorable. At greater mass, even the entire neutron star configuration can lose stability. Each threshold is different, and each one tells us something about which laws of physics are carrying the load. Quantum mechanics prevents fermions from simply collapsing into identical states. The strong interaction helps determine how dense nuclear matter generates pressure. Superfluidity and superconductivity may reorganize the behavior of particles across macroscopic regions. General relativity describes the curvature of space-time created by the star as a whole. A neutron star requires all of these ideas at once. That is why its interior is difficult. The theories are not being tested in isolation. They overlap inside the same object. For most stars, the equation of state can be connected to conditions that physics understands comparatively well. For neutron stars, the deepest layers occupy a regime where laboratory measurements, nuclear theory, astrophysical observations, and relativistic gravity must be combined. No single method can reach the center, so the center is reconstructed indirectly. A radio pulse arrives at the correct fraction of a second and helps reveal a mass. An X-ray waveform carries the signature of light, bending around a compact surface. A young neutron star cools faster or slower, depending on processes occurring kilometers beneath its crust. A sudden glitch suggests that angular momentum has shifted between internal components. Two neutron stars spiral together, and their resistance to tidal deformation changes the gravitational waves crossing Earth. The signals are different. The hidden object is the same. Over time, those measurements can force theories into a smaller and smaller region of possibility. Some candidate equations of state will prove unable to support the heaviest known neutron stars. Others may predict radii incompatible with increasingly precise observations. Some will fail to reproduce Bruce cooling behavior. Others may predict tidal responses that future merger measurements do not show. The process is less like opening a sealed object and more like determining the shape of something from every shadow it can cast. Eventually, the shadows may become precise enough that only a few interiors remain possible. Perhaps the innermost core will prove to be dominated by strongly interacting neutrons and protons all the way down. Perhaps hyperons appear once the density becomes high enough. Perhaps nucleons gradually cease to be the best description, and quark degrees of freedom become more useful. Perhaps a strong phase transition separates two forms of dense matter inside the same star. At present, those possibilities do not stand on equal footing in every model, and none should be treated as an observed picture of the core. The uncertainty is real, but it is bounded uncertainty. We already know that neutron star matter must generate enough pressure to support stars around twice the mass of the Sun and beyond. We know that neutron stars are compact enough to bend light strongly around their surfaces. We know that their mergers deform space-time in measurable ways. We know that some of their interiors behave in ways consistent with superfluid physics. We know that their cooling can be sensitive to particle reactions taking place far beneath the surface. The missing answer is becoming more specific. That matters because the center of a neutron star sits between two domains of physics that are each remarkably successful. Quantum theory describes matter and its particles. General relativity describes gravity and space-time. Inside an ordinary neutron star, both can be used without forcing a complete theory of quantum gravity. But as a star approaches its maximum supportable mass, the conditions move toward the boundary where gravity can overwhelm every available form of pressure. If collapse continues and an event horizon forms, the problem changes. The exposed laboratory disappears. What remains outside can still be studied, but the material that once carried the star becomes hidden behind a causal boundary. For that reason, the most massive stable neutron stars are especially valuable. They push matter toward the strongest gravity we can study, while a material surface still remains visible to the universe. They stand close to the line without crossing it, and that line is not merely about destruction, it is about the limits of description. At lower pressures, we can speak comfortably about atoms. Farther inward, we speak about nuclei, then neutron-rich matter, then perhaps new hadrons, condensates, or quark phases. At still greater compression, even those descriptions may need to be replaced. Physics advances by discovering where a useful description stops working and what must take its place. A neutron star gathers several such boundaries into one object. Its surface is small enough to fit inside a metropolitan region. Its interior contains densities that cannot persist freely anywhere on Earth. Its rotation can remain regular enough to serve as one of nature's most precise clocks. Its magnetic field can organize radiation across enormous distances. And beneath all of that visible behavior lies matter whose deepest arrangement remains uncertain. The contrast is easy to miss. From Earth, a neutron star can be almost nothing to look at. A point, a pulse, a source in an X-ray detector, a faint gravitational signal from a distant merger. Yet the physics behind that small observation reaches from quantum particles to curved space-time. The object does not need to be large to contain a large question. Long after the supernova fades, the remnant continues carrying that question. It rotates, it cools, its magnetic field changes, its crust adjusts, its interior exchanges heat and angular momentum. If it has a companion, matter may one day fall onto it. If it belongs to a compact binary, the orbit may slowly tighten until another merger begins. Through all of those stages, the star remains a record of what matter can endure. And somewhere beneath the crust, pressure continues to rise toward a center we cannot yet describe with confidence. There may never be a single observation that announces the answer. More likely, the interior will emerge gradually from many measurements agreeing with one another. A radius here, a heavy pulsar there, a colder surface, a better gravitational waveform, a pattern in a population of stars. One by one, descriptions that cannot match nature will fall away. What remains will tell us not only what neutron stars contain, but how matter behaves when compression reaches the edge of what stable matter can support. For now, the surface still escapes light. The star has not crossed the final boundary, and beneath that small curved surface, matter is still holding.